Hey everyone, this is just a quick video on how to use the z-table. You should have a z-table in your textbook. I didn't say specifically on which page because we all have different versions. In my version of the textbook, it starts on page 513. But you can look here, it's under Appendix C, and you want to look for tables. And there will be several tables in the appendix of your textbook, and you want to make sure that you are using the correct table. So for this video, we want to use the z-table, and I've also posted this under the modules for this week's session. So you can see a PDF version like this for your z-table. So look and make sure that you're using the z-table. So the z-table is looking at the area under the normal curve. Specifically here we're using the z-distribution. So let's say that we have a normal curve that looks something like this. So we have our curve. I know I'm not a very good artist, but imagine that this here, you have the x-axis. Over here you would have your y-axis, right? And we could draw our mean here in the center of the distribution. If we're using the z-distribution, our mean is going to be at 0. So this point on the x-axis where the mean line is, the mean of the distribution, would be at 0. And so you see this here in the table. So a z-score of 0 is at the mean, and there's certain properties about this distribution that make it valuable to us. So we know that this curve captures all the possible scores of z. So 100% of the scores would fall under this z distribution, this z curve here. We know that if we look at the area under the curve from this line here at 0, right, our mean, that we have 50% of the scores that fall in this area here, right, above the mean. We also have, as you can see here, area beyond z, 50% of the scores are falling above the mean. We also have 50% of the scores falling below the mean. We know that because our percentages have to add up to 100%, right? 100% of the scores have to be underneath this curve here. Right? With our z-distribution, 50% are going to fall above the mean, 50% below the mean. Now, how we can use this is that if we know the mean for a population, say that we know our mean is 50. If we know the standard deviation, let's say that our standard deviation is 7. If we're given a score, if we have a score of x equals 62, we can convert this raw score of x into a z-score. All we have to do is first find the deviation, which we did in the last unit. So we would take x minus our mean of 50. So 62 minus 50 would give us a deviation score of 12. And we would divide it by our standard deviation of 7 to get our z-score of, let's see here, 12 divided by 7 should give us a z-score of 1.71. So this is our measure of deviation from the mean in standardized units. And we can use this z-score and reference our z-table to determine area under the curve. So all we have to do is we have to look down here and find our z value. So we start at 0, we go down until we find a z-score of 1.71. So here's our z-score of 1.71. And then we see two values here to the right that correspond to a z-score of 1.71 in our table. We see 45.64, and we also see 4.36. So what do these numbers mean? So first we need to kind of look back at our distribution. So we can draw our x and our y-axis, we can draw our curve, and we can put in our mean, which we know would be at 0. We can think about our z-score of 1.71. It's positive, so we know it's to the right of the mean. So let's say that, hypothetically, our z-score of 1.71 falls somewhere about here. And so this line would intersect the x-axis at a value of 1.71. Now, this first value here of 45.64 would represent the area between the mean and z. So that would be our area right here. Right? So what that's telling us is that 45.64% of scores fall between our mean of 0 and our z-value of 1.71. Then the second number here, area beyond z, what that is corresponding to is the area under the normal curve that is beyond our z-value of 1.71 here. So it's all of this area here. So what it's saying is 4.36% of scores fall between this value of 1.71 and the end of the distribution. Right? Now, since we know that 100% of the scores fall under this z distribution, if we know that 4.36% of scores fall between this z value and this tail of the distribution, what if, for instance, we wanted to know, well, what scores are lower? So we know that 4.36% of scores are higher than a z-value of 1.71. What if we wanted to know what percentage of scores are lower than a z-value? It would be all of this area here. So first of all, it would include 45.64%, right? It at least include that, plus the bottom half of the distribution. Since we know that 100% of these scores fall below this distribution, all we have to do is take that 100 minus 4.36, and we would know that of the scores that fall below our z-value of 1.71, we have 95.64% of scores that fall below that value of 1.71.